Good afternoon, everyone. I am Mayank Bansal, and I'm a research scientist at Waymo. Today, I'm going to be talking about teaching a car to drive itself. We're going to walk through the design of ChauffeurNet, which is a deep learned driving network. But before we do, let's look at some examples of this network driving a real car at our test facility. Here is an example demonstrating lane following down a curved road. You can look at both the overhead view as well as the camera view to witness the smoothness of the drive. The second example demonstrates stopping for a stop sign. The car detects the stop sign, slows down, comes to a full stop, and then continues with a right turn, all of it being executed by ChauffeurNet. The change in the color of the car indicates braking issued by the net. Now let's jump right into designing this network. And in order to do that, we first need to define the scope for what this network will do. So here is a quick overview of what a typical self-driving software stack looks like. So you start from sensor data, which could come from a multitude of sensors like cameras, radars, and lasers. And then a perception module takes all that sensor data and converts it into a higher level representation. For example, where all the objects are, how they are moving, their speeds, accelerations, what is the state of traffic lights, and so on. All of this information is then fed to a behavior prediction module. This module is responsible for predicting possible futures for objects. For example, there's a car in front. Is it going to turn left, turn right, or stay stopped? Things like that. Then all of this information goes further into a planner module. This module then absorbs all this information and converts it into a higher level trajectory representation. This representation might be in the form of a sequence of poses or in some other representation. But essentially, you take this and feed it to a controls optimizer. The controls optimizer is the one which is optimizing through this trajectory to convert it to throttle and steering commands, which ultimately the controller on board the car will use to drive the car forward. Now, when it comes to actually thinking about machine learning for the driving task, we have a number of options. We can either replace each of the independent modules with ML or replace multiple of them together. One of the approaches which sits at one end of the spectrum is called end-to-end driving. In this case, you replace the entire stack with a single machine learned model, which starts directly from sensor data and directly produces throttle and steering commands. You can also do mid-to-mid driving. In this case, you produce a high-level trajectory instead of directly outputting throttle and steering commands. And instead of starting from sensor data, you start from a higher-level representation that was generated by the perception module. This is precisely the representation we'll use for ChauffeurNet. To go into more detail, here is a view of what exactly the input looks like. So the input is like a top-down view with the rendering of the perception output in the form of these white boxes. And the output will be the sequence of poses, which is our trajectory representation here. Now, there are a number of advantages to this particular representation. First, since we are using perception output, it allows us to decouple the complexity of learning a perception system from the complexity of learning a driver. Then we can also use any other perception algorithm independent of how we train the model. And finally, if we want to train and evaluate in simulation, we can do it without having to bother about how would we actually generate sensor data in simulation, because perception can actually be generated much easily in simulation. Now that we have defined the scope for this network, let's think about how the inputs and outputs will be more precisely defined. So we start with a top-down or bird's eye view. like I showed in the previous slide. In this case, we fixed 80 meters by 80 meters world representation, and our agent or the self-driving car would be placed at a specific location within this view. This is shown by the white box in this figure. Then we'll represent all the context around the SDC or the agent in the same coordinate system. So the first image shows a road map which represents all the known a priori features of the map. For instance, you see the lane markers, the center line shown as yellow, the crosswalks in blue, and we can add a lot of features like stop signs, the presence of traffic lights, and so on in the same map. Now, when it comes to traffic lights, we need to convey to the net what is the state of traffic lights. This is again being generated by the perception system. In this picture, we show how we represent that. These are all center lines of the lanes in the same grid as the map, and the intensities encode the traffic light states. So in this particular example, the brighter shades would reflect red light, and the other shades would reflect green light. This is the speed limits channel, again encoding different speeds with different intensity profiles. Now, the perception objects which we talked about before, in this case is a sequence of images. We want the net to know exactly how they were moving over the past time frame. So we have a sequence of images going from the past 1 or 2 seconds. And for each of those time steps, we'll have a single slice of the sequence, which shows all the objects in the scene as these bounding boxes, which are colored white here. In the similar representation, we also want to show how exactly our agent was placed and its heading, which is shown by the white box here. Now, to convey how the agent actually was moving in the past, we also have a channel which shows a sequence of dots. Each of these pixels is the location of the agent over the past, some time step in the past. And finally, we want to convey to the net exactly what we want the agent to do. So this is the planar route channel, which conveys that. So if you look at it closely, this is essentially a Google Maps style representation, which shows that we want the agent to actually turn right in the next few seconds. Now, given all this information, we want the net to output a trajectory. As I said before, this trajectory is in the form of these waypoints, which are shown by this animated set of green dots. Now we have defined the scope as well as the inputs and outputs. The next point here is to actually pick up a model architecture. For our first model, we'll use a convolutional recurrent neural network. So this is a high-level schematic of what this network will look like. So if you follow the picture with me from top to bottom, you start with the rendered inputs. You pass them through a set of convolutional layers, which is shown as a feature net here. That produces an embedding of all the inputs the net has seen, and that gets passed on to agent RNN. This agent RNN is actually the recurrent part of the net, which is responsible for producing a sequence of waypoints, which together form the trajectory. Now, for each of those waypoints, you want some metadata, which is shown by these different arrows with heading, speed, as well as what the box looks like at each of those waypoints. And as you can see in the bottom part of the picture, all of these predictions are guided by the ground truth known from the log data and are driven by usual losses. Now, to look at it in a little bit more detail, this is a blow-up of some parts of the network. If you focus on the output of agent RNN, on the top right, you can see a predicted location PK. Now, this predicted location PK is one particular output. You actually produce that and then update a memory M. This memory gets fed back into the agent RNN, and the agent RNN can then use this to produce the next waypoint. On the bottom right, we show what it does for the agent boxes. It has a similar recurrence to produce a sequence of box locations. So in essence, the agent RNN is taking in all the input data and conditioned on whatever it has predicted till now, it's actually predicting the very next waypoint. And in this way, it can predict the entire trajectory. Now, once we have this model, we generate our training data by sampling 26 million examples from lots of our driving logs, and then we train the model. Now comes the interesting part. Now that we have a model trained, the question is how exactly do we evaluate it? Unlike traditional ML models, in this case, we want this model to be able to drive the car. So it's important to pay attention to exactly how we evaluate it. As I'll discuss next, there are two approaches in which we can evaluate this model: open loop and closed loop control. So this is the traditional way in which you typically evaluate models. In the diagram here, you take the logged poses as well as all your input data for a given test example. You feed it through the net, and then you predict the waypoints and compare them to the ground truth to actually get an idea of how well the network is performing. But if you really want the net to be able to drive the car, you need to think about it in a slightly different manner. That brings us to closed loop control. So in this case, once you have the predicted waypoints, you actually feed them to a vehicle simulator. Think of it as a simulation of the vehicle dynamics. In practice, in reality, this will be the actual vehicle taking in those waypoints. Now for evaluating in simulation, we'll use the vehicle simulator, which will use these waypoints to drive the car forward. Because of that, the car might actually drive forward and generate new poses. Now, an interesting aspect of this is that those poses might be very different from what the net was trained with. Now, given that, it would be really hard for the net to generalize if it has never seen this data or it actually lands outside its distribution. So it's important to evaluate the network both in open loop as well as closed loop settings. So let's look at what our network does in our very first test. So the very first test is the simple task of lane following. We find that it's able to follow lanes seamlessly in open loop, but in closed loop, it goes off-road. Now let's look at why that is. So here is a single test example. Blue dots are the past, and red dots are the future locations predicted by the net. You can see that these locations are well aligned with the lane boundaries, which shows that the agent did a good job using this net as a driver. Now consider these other two examples. These were generated in closed loop setting, where the lane lines had a slight offset in the angle relative to the image coordinate system. As you can see, the red dots are no longer aligned with the lanes. In fact, they are taking the car off-road. Closer attention in these green boxes shows that the red dots are more or less aligned with the image axes. So what's happening here is that the net has learned a bias from the top-down orientation of the input data. All of our input data was rendered with a specific orientation, and the net has learned that that orientation is much more important than the lane orientation. So we really want the net to be able to learn what it is like to drive along the lanes and not along the image axes. So what we do here to resolve that is to actually render the training data with a whole bunch of randomized heading offsets. So here are 3 examples of different ways in which we have oriented the input. So when it goes through the training pipeline, the net can actually focus on the lane orientations. So this is one example of the kind of domain-specific perturbations we might need to actually make the ML system work. Now the next task that we evaluated the net at was related to stop signs. So once again, we find in open loop, the agent stops for a stop sign. But in closed loop, it actually never stops and continues driving past them. Now this one is a little bit more interesting. So if you consider what's happening in most of our training data, we find that most of our training data has past motion profile, which is already braking for the stop signs. So the agent is already braking for the stop signs when it comes into its field of view. Now because of that, the net doesn't actually learn that it has to slow down for a stop sign. It rather learns that if it just purely extrapolates from the data, it can come to a stop sign. Now if you apply the same analogy to the closed loop setting, we find that in most closed loop examples, our agent is actually approaching the stop sign at a constant speed. Now because of that, the net again extrapolates, continues driving at constant speeds, and just runs off the stop sign. So once again, the important point is the net has learned a bias, this time not from the way the data was generated, but just from the characteristic of what it is being fed. So the bias in this case is from the past motion, and we really want to remove that to be able to avoid this bias. But the issue is, it's important for the net to know what speed and acceleration the car was driving with, so it can actually predict the future. So we can't really remove that past motion. Instead, what we do here is we propose adding a dropout on these poses. What that means in practice is that for a subset of examples, we actually remove the past motion, but we do keep it for the rest of the examples. And that lets the net actually learn that to explain the stop sign, it has to really look not on the past poses, but on the real things which are rendered into the input. Now we found the agent followed lane lines. It came to a stop, but now an interesting problem came up. It never moved after that. It really got stuck. Again, this difference was pretty evident between open and closed loop evaluation. And unlike the other two cases, this really has to do with the way we have modeled the problem. So we are using a recurrent neural network to actually predict the successive waypoints. But if you consider the problem of what happens when you want to really move the agent from a standstill, you really need to focus on the first few waypoints, adding an incremental amount of motion. Now the RNN, in our case, doesn't know which waypoint it's predicting. So the very first waypoint it predicts has a small motion, which might be sub-pixel, and it doesn't move the agent forward at all. Next time through, it again sees that the agent is where it was, and it again issues a small motion. Compounding that together, the agent never moves. So in essence, the RNN keeps predicting less than 1 pixel motion, and that's not enough to move the agent forward. So a solution to that, in this case, was actually modification of the network itself. If you focus on this K, the teal box that we have added, it tells the network what waypoint it's actually predicting. So for the first waypoint, it knows it's the first one. And by, let's say, the fifth waypoint, since it knows it's the fifth waypoint, it can issue a bigger motion, irrespective of how much it has moved till now. And that gets it unstuck. Till now, we have looked at a number of issues we saw in the model, and for each of those, we saw a number of ways to resolve them. For orientation bias, we looked at data augmentation. For motion bias related to the past motion, we looked at input dropout. And then for an issue with the model architecture itself, we had to improve with the model itself. Now that we have this model, we'll call this as an imitation model. That's because we've used purely supervised data to train this network. Now let's look at what happens when we actually evaluate this model in a closed loop setting in a more complex scenario. In this video, pay attention to the gray box, which is the agent being driven by the imitation model. As it continues driving, we find that it drifts and lands on top of the yellow line. So the agent is not able to maintain its trajectory, and over time it slowly drifts. But because there is no way for the net to actually know how to correct these mistakes, it's not able to recover. So in this case, we again need some sort of mechanism to teach the net this recovery, but it cannot be done simply by augmenting the data the way we did before. So consider this training example. Here the red dot is the current location of the agent, white dots are the past poses, and green dots are the future that we want the net to predict. Now we take this example, we shift the position of the agent, which is the red dot, randomly along one direction, and we fit another trajectory through the red dot and the first and last points to generate a smooth profile. If you look at this animation here, you can see that the profile of the perturbed image is actually a feasible driving profile, and it's really telling the net that if you ever land up in this situation, how do you actually bring the agent back to the center of the lane? So we can do this with random amounts of shifts for all our training data, and given both our original as well as perturbed examples, we can train the net to basically learn from both the original data as well as the perturbations. Here is a test example of a perturbed example set. The second image shows what happens with our original model, which did not know how to recover from perturbations. So in this case, you see that the agent goes off-road because clearly it has no idea how to bring it back. Now this is the result of the model which was trained with perturbations. So as you can see, it's not completely reflective of the ground truth, but it achieves its goal of actually bringing the agent back to the lane center. So now we'll revisit the example we had before of the agent going around a turn and where it landed on top of the yellow marker. So as we saw here, the agent no longer lands on top of the yellow marker. It's able to issue small correction commands to actually keep it well aligned in the center of the lane. Now we have our imitation model, and it's able to perform lane following even over longer scenarios. But are we done yet? Sort of. So we find that it's able to avoid collisions in most cases, but it doesn't have the generalization ability to actually avoid collisions in new situations. So here is an example of an agent approaching a parking area where you will see a car pulling out of its spot. And as you saw here briefly, the agent passed right through the unparking car. So the agent has learned to avoid collisions, but clearly not general enough to face these situations. And this situation is rare enough to not be present a lot or even at all in our training data. So how do we fix this? So going back to the architecture diagram of our net, we really want to teach the net explicitly what it is to avoid collisions. So we do this by adding a loss that explicitly measures overlap of each prediction with the rest of the scene. So if you focus on the inset here, the yellow box is the agent which is predicted at a particular time, and the blue boxes are the bounding boxes of all the other agents in the scene known from ground truth. Now if you overlay these boxes together, you can get a fair idea as to whether the agent has any overlap with the other objects. And if there is an overlap, that should drive a loss function to actually update the model weights to not perform the action that generated this overlap. We can do a similar thing to avoid collision with road edges like curbs and so on by painting the road edge in a view and then overlapping it with the agent to test this loss. Now this is good in theory, but in practice this does not actually solve anything. The reason being that our training data has no collision examples. Our training data came from expert driving, so there were no collisions, and hence if you look at these losses, they'll always be 0 and would not update any gradients. So for us, the only reason it works is because of our perturbed examples. So if we look at any of our synthesized perturbations, we have made no attempt to actually resolve collisions. So lots of those perturbations will actually have synthetic collisions, either with the road or with other objects. And all of those synthetic collisions will actually have a non-zero value for this loss. So using those synthesized perturbations, we can actually make the net use these losses throughout training. So let's look at that example again of an unparking car, but this time after having trained it with the collision loss. Once again, the car is approaching that unparking zone, and it sort of drifts over and nudges around and avoids collision with that car. Okay, so far we have the net which can avoid collisions, drive smoothly through the lane boundaries and so on. But we want to do even better. Typically in machine learning, a way to improve generalization of any models is to co-train with other objectives which might be relevant to the main task. For the task of driving, one such task is to predict the future of other agents. As we saw in the architecture diagram for self-driving software stack, behavior prediction is an important module. What if we could predict the future of other objects together with predicting our own trajectory? This is precisely what we do with the addition of another network here that's shown as perception RNN in this image. This is again a recurrent neural network, but instead of predicting our own future, it predicts the future of all the other objects in this scene. If you pay closer attention, you can see that this particular output is also driven by the same set of target boxes which we used for measuring collision. So in this sense, using the same labels, we can drive this co-trained output as well. And because this particular RNN is branched from the same feature net that we use for agent RNN, it can actually improve the feature net and lead to better performance for the main task as well. So these are two examples of what the predictions from perception RNN look like. So the red and yellow boxes are the past boxes or the past perception objects, and the green trails are the predictions from this net. So it's pretty good in terms of predicting U-turns as well as figuring out the intents of other objects when, for example, they are in a right turn lane, whether they are actually going to make a right turn or continue straight. Now we can also do the same thing for the road mask, which is essentially a bitmap of drivable and non-drivable areas. This is not RNN because we just want to know in the current map which area is drivable and which is not. And this is another co-trained output which we use to actually drive better features and then better performance from agent RNN. The final piece of the puzzle that I'm going to talk about is called imitation dropout. If you focus on the losses that we added, which are in the green box here, these are all meant to imitate what exactly the agent did in the log data. In essence, these are all imitation losses. All the other losses that you see here are meant to just test or infer how exactly the agent is coordinating with the rest of the environment. Now, in order to make the net generalize better, we want to give it some freedom to explore, even when it doesn't want to imitate whatever was given in the logs. So to do that, we add an imitation dropout. What that means is that for a random subset of our training examples, we actually remove these imitation losses, and the gradients are driven entirely by the rest of the losses. So for those examples, the net is free to explore whatever alternate trajectories it wants to, and then the only basis for them to be correct is that they should interact correctly with the rest of the environment, which is driven by the collision loss, road mask loss, and so on. And just empirically, we found that this particular strategy works much better than simply reweighing between the losses. Till now, we have looked at how the model behaves, and we have shown some example videos of how we can debug it. But for a complex model like this, we would typically want a better strategy, and ablation experiments is one such strategy to confirm what the model has actually learned. So here's a scenario where we have drawn a stop sign with the red blob. We have taken this same scenario and we've removed the stop sign during the rendering stage to generate this scenario on the right. Now we'll take both scenarios and run our net on both of them. And if it's actually learned the meaning of a stop sign, it should behave differently between the two. So you can see on the video on the left, the agent comes to a full stop behind the stop sign and then continues after a short wait. If you look at the video on the right, you can see that in the absence of the stop sign, it merely slows down in anticipation of the turn and then continues. We can perform the same experiment with vehicles in this scene. On the left is this scenario with all the original vehicles, which are shown by these yellow boxes. On the right, we have removed these yellow boxes to simulate the absence of any traffic. Once again, if we focus on these videos one by one, on the left, the car sees these stopped cars, it waits behind, and it does a stop and go as expected. On the right, in the absence of any traffic, it behaves in a completely different manner because there's no reason for it to stop for anything, which shows that the agent has really learned what we intended for it to learn. Now we can perform the same test at the model end to really figure out what is the difference between the different models that we have built. So here's a scenario we created where we put a parked car in the middle of the road and have our agent approach it. We find that our car starts off well, but as soon as it sees this parked car, it slows down and comes to a full stop and gets stuck. So this is the result from our imitation model, which doesn't have the other techniques built in. Now if we repeat the same test with the full model, we find that the agent is again able to nicely nudge around the parked car and continues to make progress. This second scenario illustrates again recovery from trajectory perturbation. So we put our agent at a slight heading offset, approaching a tight curve, and we find that on the left, the imitation model once again gets stuck, not knowing how to recover, while the full model is able to recover nicely and continue along the path of the entire turn. The final scenario is that of a slow-moving vehicle. So we put our agent at the speed limit of the road approaching a car moving at a much slower speed, and we want to see how it generalizes. The imitation model slows down for the slow-moving car, but ultimately it keeps slowing down until it gets stuck. The full model, on the other hand, is able to adjust its speed and then continues making progress in a typical cruise control fashion. Those were examples of some of the log data. Let's look at some more of these logged driving examples. So this is an example of approaching traffic lights. Once again, if you recall, the lane center lines encode the state of traffic lights. In this case, the traffic lights turn from orange to red, and the cars in front escape the light as expected. But our agent, instead of just following behind them, it comes to a stop for the red light and then continues as it turns green. This next example shows stop sign handling, which all of you are familiar by now. But the interesting part is the car is coming out of a cul-de-sac. It sees a number of parked vehicles. It's able to nudge around, make way for itself, and then continues and stops for the stop sign. So the key point here is these are all scenarios with different levels of complexities, and we can't expect all of them to be present in our training data. So we really need to teach the net to generalize to be able to handle these. This final example shows a stop and go situation at a traffic light. The agent comes behind a stopped car, stops, and as the light turns green, instead of again stopping just like the other car, it continues very naturally. Before we wrap up, I'd like to showcase some of the current issues with the net. The very first issue that we see has to do with the way we have represented the input. So our input is a fixed 80 by 80 meter representation, and that basically removes a lot of possibilities in terms of what the agent can see. So in the first video, I'll show here the agent is approaching a turn on a fast-moving road, but because it can't see the turn soon enough, it's not able to execute that turn. So I believe this is a 45 miles per hour road. The yellow box shows what the car actually did in the log, but our agent, being too fast for the turn, simply gets hit. The second example is one representative example of a rare event. For example, U-turns, which are not present frequently enough in our training data, and so we can't expect the net to actually be able to generalize well to new situations like that. So in this case, the agent, which is the green box, will again try to execute the route, but will fail to do so. The yellow box was the box in the log, which correctly did this maneuver as expected. And finally, lots of highly interactive situations which we encounter every day during driving. For example, during lane changes and merges, those all involve a lot of social interaction, for which the net really needs newer features, for example, to be able to use reinforcement learning or a real simulator where you can simulate these interactions. In conclusion, what we talked about today is essentially that in order to solve the driving task, it's not enough to have tons of logged driving data, and that we really need lots of task-specific techniques to really simplify the problem and to help the net everywhere possible so that it can generalize across away from what it has seen in the data. For more details about this work, please see our paper as well as the associated website. Thanks for all your interest. Thank you.